Perfect. Okay, so most of what we do in SIL verification is probability of failure on demand. And we have equations that we use in the ISA training that are mostly correct. They are partially wrong. I will explain why they are partially wrong and which components are wrong. So that's why these equations in some instances don't match up exactly with what you'll see in Vertigo. What is in Vertigo is correct. So in order to understand these equations, let me draw it out first. So for 1 out of 1, the equation is lambda dd times mttr plus TIA over 2. And that's the first term, which I'm going to call the DD term, or the dangerous detected term. And what it represents is the unavailability of the safety instrumented function, or the component of the safety instrumented function, because it has failed in a dangerous way, but that dangerous failure has been detected, but the safety instrumented function is configured to continue to allow the plant to operate in the presence of the failure and wait for it to be repaired. So this is an unavailability of the safety instrumented system component while we're waiting for it to be repaired, the DD term. The next term is the DU term. So this is going to be lambda DU times the test interval over 2. This is a standard unreliability. So 2 different terms, unavailability, unreliability. I'll also call this the DU term. This term is related to the unreliability of the safety instrumented system due to failures that are not detected with automatic diagnostics. You will not know about them until the safety instrumented function fails. That term is always there. That is the one term that is never ever going to go away. And you'll see this is in the format of lambda t over 2, whereas this is in the format of lambda mttr. I will come back to that. The next term is the lambda dn term. So we have lambda dn times life over 2. This I'm going to refer to as the dn term, or the never detected term. You'll see by its format, lambda t over 2, that it is also an unreliability, not an unavailability. The difference here is, put the D in there, DN. The failure rate is the rate of those failures which are never detected. So this lambda DU, we expect this portion of the dangerous undetected failures to be detected when you do your offline manual proof test. But this portion of failures will never be detected no matter how often you test it, because the testing processes are incapable of detecting that that type of failure has occurred. So a good example of a never detected failure would be if I am using a diaphragm type actuator to move a shutoff valve, and that diaphragm starts to have pinhole perforations on it. That means that the pressured part is leaking through to the unpressured part, but only a little bit. Well, there's a point in time where those pinhole perforations are going to start to decrease the amount of force that that actuator provides. Now, when you're offline and you're testing that valve under no pressure, it might move just fine. But then when you bring the process online and you try to stroke that same valve when it's under process pressure, there might not be enough force to cause it to move. So that is the types of failures that would never be detected even with manual proof testing. Just some rough numbers. We generally expect for a smart transmitter to have about 99% manual proof test coverage and a valve system about 95% coverage. But lambda DN is real, and it's something that we need to account for in our calculations. And again, this is an unreliability. The last term, and I'll just add it here, is it's going to be the test duration divided by the test interval. And this actually is also an unavailability. It is downtime over total time, and that's the format that we use when we're doing an unavailability. This is going to be, I'll call this I generally call it the online testing term, or it might be called the TD term, but often online testing is used. So when we're calculating the overall PFD of a 1-out-of-1 or a simplex system, we need to evaluate all of these terms. But if you look at, for instance, the early version of ISA 84's technical report on how to perform PFD calculations, it only contains this one term and none of the others. So why is that? Well, you can zero some of these other terms out, and that's what they did in the early versions of the technical report. So if you don't have any diagnostics, then lambda DD is 0, this term goes away. Or if you do have diagnostics, but when you detect a dangerous failure, you cause your SIS to go to the shutdown state, to move to the safe state, then the amount of time that you're operating with the plant in an unavailable mode, or the safety function in an unavailable mode while the plant is running, is 0. So what you're doing there is you're essentially taking this lambda DD and shoving it over to the other side of the ledger and converting it into a lambda S, or a safe failure. So that's what would make that term go away. The DU term is always there, it never leaves. The lambda DN term historically was kind of ignored because the guidance from the industry professionals and practitioners was, we want to make sure that our proof tests are as close to 100% effective as possible. Therefore, we're going to ignore never detected because we assume 100% of the failures are detected. It's not that bad of an assumption, but I think we've gotten to the point where we really just can't ignore it. So most of the time, you're really going to want to see this lambda DN term. Okay, so that assumption that you have 100% coverage is generally not true. The online testing term is only applicable if you do online testing. If you do all of your tests offline during a turnaround, the duration that you're in bypass while the plant is in operation to test the safety system is 0, which makes this term 0 and makes it go away. So now, those are what the terms are, and this is for a simplex 1-out-of-1 system. Where did these terms come from? And I've mentioned the word unreliability and unavailability. So let me go and clearly define what I mean by those terms. So I'll define what the term is, and then I will mathematically represent it. Okay, the first term is going to be unreliability, which is the complement of reliability. So first off, what is reliability? Now, I'll give you the light bulb analogy or explanation of what reliability is versus availability. Because when you're talking with people in industry, when they say reliability or availability, more often than not, they are using the term improperly. So now let me give you a little bit more of a precise definition. Reliability is the probability that a device will operate for a given mission time. The key thing to remember about reliability is we don't care about the ability to detect or repair failures in the middle of the mission. So if I had a light bulb in a closet, so I open the door to the closet and I put a light bulb in, turn the light on, and then I'm going to close the door, leave, come back a year later, open the door, what is the probability that the light bulb is still lit? That is the reliability. And reliability mathematically is going to be e to the minus lambda t. I'm not going to go into a further definition of where this came from. It's basically a time summation of a constant probability density is where this term comes from. That's where the definition of E came from. Now this term, it looks easy enough, but we're going to be doing calculus with it in a few seconds, so we're going to want to simplify it. Furthermore, we don't care about reliability because we're pessimistic safety system engineers. We care about unreliability. So we don't care about the probability that it works, we care about the probability that it fails. And unreliability is the complement of reliability, or 1 minus e to the minus lambda t. Now, this term has exponents, it's got e, it's got all kinds of things that are going to make integration tough. So I'm going to simplify this by saying that the unreliability is approximately equal to lambda t. And I can say that because lambda t is actually equal to an infinite series called the Maclaurin series, where the first two terms are 1 minus e to the minus lambda t, and then there's a plus and a minus, and you start putting exponents and getting infinitely smaller terms as you expand this series out. So lambda t is exactly equal to the infinite series. The approximation comes from the fact that I am going to basically, I'm only looking at the first couple terms of the infinite series. So lambda t is what the term that we're going to use. Now, if you look at a time series, and you have to look at a time series, this 1 minus e to the lambda minus lambda t is going to look something like this. The ISA 84 IEC 61511 standard said that I don't want to know what is the ultimate. So if the test interval is out here, I don't want to know the unreliability at that point in time. I want to know what the average unreliability is over this entire duration. So in order to figure that out, we're going to have to do a little bit of calculus. So if I want to know the average, then I need to calculate the area under this curve, and I need to divide it by the total duration, the total time. So my average unreliability is going to be equal to the integral from 0 to the test interval of lambda t dt. All of that over the test interval. So now I'll start doing some math. Let me pull my constant out in front. So 0 to ti of t dt over ti. Then I'll do my integration, and that's going to be lambda times the quantity of t squared over 2, and that's going to be evaluated from 0 to the test interval. All of this again over the test interval. Then I can expand that evaluation, so I'm going to have lambda ti squared over 2 minus 0 squared over 2. All of that, again, over the test interval. And then that will, if I knock that 0 out, now I've got lambda ti squared over 2 over ti. Simplify by taking that ti out of the denominator, knocking the square out. Lo and behold, I've got lambda test interval over 2. So this lambda ti over 2, that's going to be the average unreliability over the entire test interval. So that's where that unreliability term came from. Next up is unavailability. So let me get rid of some of this and run some more math for you, because everybody loves math. Math on a Friday morning, nothing better, along with my McDonald's coffee. So as I was putting the terms up on the board, I showed that everything was either an unavailability or an unreliability. So now you see where the lambda t over 2 for an unreliability comes from. Where does the term that we always use to describe unavailability come from? And that term is going to be lambda mttr, where mttr is the mean time to restore. So the mean time to restore includes detecting that a failure has occurred and actually performing the repair. So where did this come from? I said it is an unavailability. So let's start with availability. What is the definition of availability and how is it different from reliability? Let's go back to my light bulb in the closet. So before, I took the light bulb, put it in, shut the door, left, came back a year later, opened the door. Is it working or is it not? No concern about detection, no concern about repair. Availability, though, is all about detection and repair. So now, I'm going to take that light bulb, I'm going to put it in the socket, I'm going to turn the switch on, but I'm not going to leave. For the next year, I'm going to sit and I'm going to watch the light bulb. And I'm going to watch it, and I'm going to watch it, and I'm going to watch it, and I'm going to wait for it to fail. And when it fails, I'm going to take that light bulb out, put a new light bulb in, and continue to sit and watch it. And there's going to be a sequence of devices operational, it fails, it's repaired, and then it's operational again. The availability, and now we need to make our infamous triple equal, is defined as the uptime over the total time. So that means how long is the light bulb lit, considering the fact that it fails and it's repaired. That's availability. The complement of availability is unavailability, which is downtime over total time. Okay, well, wait a minute. We already used U for unavailability or unreliability. So now we need a new variable. So industry has decided we're going to go with Q. So Q is our unavailability, and it's the downtime over the total time. Now, that last term that you saw for the online testing interval, that's exactly what we're talking about here. The test duration is how long you're down, And the total time is the mission or the test interval. Unavailability. Very strict unavailability. But we see this more often. So what is this? Where did it come from? Okay, that came from the fact that we're going to start using our terms to describe downtime and total time. So what is downtime? How often, how long are you down? Well, you are down for the mean time to restore. When something fails, you're down for as long as it takes you to fix it. What is the total time then? Well, the total time of one sequence will be how long was it in operation? Well, it was in operation for the mean time to fail. And it was then you need to add the mean time to repair to give yourself one entire cycle. Seems easy enough, like we should be able to use this, but alas, we have this plus sign in the denominator, which is going to screw up all of our calculus that we're going to be doing later. So we need to get rid of that by doing an approximation. And what our approximation is, and I'll just state it, we are going to do an approximation because we believe, our assumption is that the mean time to fail is much, much greater than the mean time to repair. Because the mean time to fail is much, much greater than the mean time to repair, then because of that, the mean time to failure is approximately equal to the mean time to failure plus the mean time to repair. Okay? We're going to substitute then this term back into that unavailability equation, and then we're going to come up with Q equals mean time to repair, or it's approximately equal to the mean time to repair over the mean time to failure. Still haven't gotten there. The other thing, just a simple substitution, is that we know that for the constant failure rate regime, the failure rate is equal to 1 over the mean time to failure. So when we replace 1 over mean time to failure with lambda into this equation, we know that Q is approximately equal to lambda times MTTR. Okay, so this is the term that we're going to use for the dangerous detected failures, unavailability due to dangerous detected. If you remember from our worksheet, that was lambda DD times MTTR plus test interval automatic over 2. So between this definition and this term that we use in the equation, what we did was we expanded. Because here, the MTTR is the complete mean time to restore, which includes how long does it take to detect that a failure occurred, plus how long does it take to repair. If you're looking at a smart transmitter or a PLC, you can ignore this part, because the automatic test interval is like 100 milliseconds in comparison with 72 hours. It just goes away. But when you're doing something like partial stroke testing that happens once a week, now you can't ignore the automatic test interval, because most of the mean time to restore is waiting to detect the failure as opposed to performing the repair itself. So this is where all of these equations came from. Term 1, the DD term, is your traditional unavailability. Term 2 is your traditional unreliability due to undetected failures. Term 3 is your never detected, which is still an unreliability. And then the last term is this format of the unavailability equation. And that's the online testing term. So that's where the first row came from. 1 out of 1. Next row up is 1 out of 2. So 1 out of 2 is going to get interesting because now all we're doing is taking our two definitions. Let me remove everything from here other than the basic definitions. So I've got my basic definition of unavailability, and then I have my basic definition of unreliability. When we start looking at redundant architectures, now we start using probability math. Probability addition, probability multiplication. And I'm going to help visualize the logic by putting things into a fault tree. So for 1 out of 2 voting, the probability of failure on demand requires an AND gate. So I have an A transmitter and I have a B transmitter. The result of the AND gate should be the result of the system. Now here is where I run into a problem, and this problem we're going to call the average before logic, average after logic problem. If I look at my average unreliability, I would say, well, this is lambda t over 2, this is lambda t over 2. Probability multiplication, because I have an AND gate, it's a logical AND. The system will fail if the A transmitter and the B transmitter fails, would lead me to believe that I just multiply these two things together. So I would get lambda squared t squared over 4. Oh, wait a minute. I'm going to look at my equation sheet and it's going to say lambda squared t squared over 3. Is the equation sheet wrong? No, the equation sheet is not wrong. We have made a small, simple error in thinking about this. Because what we did is we took the average here, and then applied our logic to the averages. Well, this is average before logic, and average before logic is wrong. Instead of averaging before logic, we need to average after logic. All right, so how do we do an average after logic? So if I don't look at the average before logic, I want to look at just kind of at any point in time, what is the unreliability? I know that lambda t is my unreliability at any point in time. So lambda t. So I know that at any point in time, my overall unreliability will be lambda t, well, let's just call it lambda squared t squared. So now, remember that calculus that we did to come up with lambda t over 2? We now need to do it to this guy. So for our 2 out of 3 system, if we average after logic, which means we're going to do our integration on the result of the AND gate as opposed to the inputs of the AND gate, it'll be lambda squared t squared dt. Let me make this a small t to keep things clear. All of this divided by the test interval. Fancy calculus. So take the constant out. All of that over ti. And now I do my integration. I'm going to have lambda squared times the quantity of 1/3 t cubed evaluated from 0 to the test interval, all of that over the test interval, and that's going to be lambda squared 1/3 ti cubed minus 1/3 of ti, I'm sorry, it's not ti, 0 cubed, because we're going from ti to 0, all of that over ti. This term goes away, and we end up with lambda squared 1/3 ti cubed over ti. This term out of the denominator cancels one of these up here to make it squared, and we're left with lambda squared ti squared over 3. So that's where the difference comes from, and that also informs you that if you do traditional gate-by-gate math, your AND gates are going to give you an incorrect answer, and it's going to be an optimistic, unconservative answer. But don't worry, if you're using the Kenexis Arbor software, we do the correction for average after logic automatically. You don't need to worry about it. You can just put in a traditional fault tree and it will correct everything. It will calculate everything the proper way for an average after logic system as opposed to an average before logic system. So, continuing on in the equations, that's where the lambda t over 2 came from for the du term for 1 out of 2 voting. For the lambda dd term, I'm not going to derive it, but basically it's just doubled because you have 2 devices. And the lambda dn term is going to use the same equation as the lambda dd term. I'm sorry, the lambda dn term is going to use lambda squared t squared over 3 because it's going to be treated the same as the lambda du, the dangerous undetected. The test interval term, or the online testing term that you see here, is not what we have in Vertigo, and I don't recommend that you use it. I recommend that for any configuration, whether it's 1 out of 1, 1 out of 2, 2 out of 2, 2 out of 3, you simply stick with test duration over test interval. The reason is when you're doing this testing, for more advanced systems, you're probably going to test one device at a time, so you're never going to be completely unavailable at any point in time during the test. Now, what the equations show, when these equations were derived, somebody went a little bit too crazy with their mathematics without thinking about physically what's actually happening. So what that equation for online testing represents is the probability that, assuming tests happen randomly in time. So first off, that equation assumes that we're not going to test both transmitters in a 1 out of 2 vote at the same time. It assumes we're going to test them at different times, and the time that we test them is completely random. So what that equation actually calculates is, if I test my 2 components in a 1 out of 2 system at random times, what is the probability that by accident I will be testing both of them at the same time? Nonsensical. So to be conservative, just take test interval, or test duration over the test interval. That is the most appropriate way to do it. And what this represents is that when you perform the test of a 1 out of 2 system, you're going to have both of the devices in bypass for the entire test duration, which is a conservative assumption, giving you a pessimistic calculation for PFD, and that is the assumption that's used in the Arbor software as opposed to the equation that you see here. The last term is new for systems that have a degree of fault tolerance against dangerous failures. That term is, it's either going to be called the common cause term or it's going to be the beta factor term, and it shows up appropriately in 1 out of 2 voting and 2 out of 3 voting. It shows up, in my opinion, inappropriately for 2 out of 2 voting. I'll explain why in just a second. So what the beta term is that it's beta times lambda du test interval over 2. Lambda t over 2 tells me this is a unreliability, and the difference between the beta factor term and the normal du term is this beta multiplier. So beta is the common cause factor, or it's the fraction of the time that a single stressor will cause all of the components, all of the multiple components in a redundant voting arrangement to fail at the same time for the same reason. So this beta factor term is going to be applied uniformly, whether it's 1 out of 2, 2 out of 3, 1 out of 3, 1 out of 4, 2 out of 4. You're always going to be beta lambda t over 2. And in the more sophisticated voting arrangements, this term is going to generally dominate to where if all you calculated was the beta factor term, you would be close enough to the actual answer that you could ignore everything else. So that's the driver. Okay, so that was 1 out of 2. Let me talk about 2 out of 2. So the most important term that we're always concerned about with 2 out of 2 is going to be the DU term, dangerous undetected. So now we're going to go back into our fault tree, but instead of an AND gate, now we have an OR gate. The system will fail if either the A gate fails or the B gate fails. And I know that I'll go back to my average unreliability of lambda t over 2, lambda t over 2, which is going to result in 2 times lambda t over 2. Cross those out, and I've got lambda t. Awesome. Well, in this case, when I look at the equation, it also says lambda t. What happened to my average before logic, average after logic problem? Well, when you look at it, the average before logic, average after logic problem does not apply to AND gates. It only applies to OR gates. So let me break down why that would be. So if I go back here and call these guys lambda t again, and I know that my result here is going to be 2 lambda t. When I do my integral from 0 to test interval, actually I don't even want to do that. I want to leave it as lambda t plus lambda t, which makes it a little bit easier to think about. So I've got lambda t plus lambda t dt over the test interval. And the first thing that I'm going to do is, because of transitive, communicative, I can't remember what the property name is, but basically because we have an addition here, this is going to be equal to this plus this. okay? Because we're adding instead of multiplying, we can separate these things out, and this is exactly the same thing as we had for our 1 out of 1 voting arrangement. So when you're doing your probability math, if you see an AND gate where you're doing probability addition, you don't need to worry about average after logic or average before logic. So that's why lambda squared t squared, I'm sorry, not lambda squared t squared, lambda t is going to be the answer that you want for 2 out of 2 voting. As usual, looking at the rest of the terms, the never detected is going to match the same equation framework as the dangerous undetected. Once again, ignore what this equation says about the diagnostic test interval math. Just use test duration over TI. Lambda DD term is using typical probability math. And the beta term is the term that is the problem. Now, why does this have a beta term? Why should you use a beta term? Does the beta term make sense for 2 out of 2? The answer is no, most of the time. Now, we don't, in Vertigo, add a beta factor to 2 out of 2 because we are adding insult to injury. Let me explain. So when we calculate the beta factor term, what we're saying is if I have a set that is the dangerous undetected failures, the beta factor is going to be a portion of those dangerous undetected failures. If I were to be perfectly correct, my lambda du that I use here should remove these failures, but it doesn't, because not removing this little slice from the lambda du that we put into the unreliability equation is a conservative assumption that makes the math easier to do. Now, if you did actually remove this, and let's call this lambda du normal, and then lambda du common cause, and that's lambda du with lambda du common cause being beta times lambda du. If you actually removed lambda duc from dun, then you would need to use the common cause term to add it back in. And lo and behold, when you add these terms together, you just end up back at lambda du test interval over 2, back where we started. So because we never remove the common cause failures from the normal failures, we cut out the middleman, ignore that term, and leave it there. So the equation that you see for common cause failures in the 2 out of 2 voting is excessive. You're if you don't remove the common cause failures from the normal, you're double counting those common cause failures. You're counting for them in the normal, and you're also counting for them in the common cause terms. So you're adding insult to injury, making it much more pessimistic than it needs to be. So in our Vertigo software, we're not going to add that in. The 2 out of 2 voting does not have an additional beta factor component. Now, 2 out of 3. The only term that I'm going to deal with 2 out of 3 is the du term, because the same kind of thought processes apply to everything else. So with 2 out of 3 voting, and let me simplify the fault tree to some degree. with 2 out of 3 voting, I am going to have an OR gate with 3 AND gates under it. The first AND gate is going to be the probability that A and B fail. The second is going to be the probability that B and C fail. The third is going to be the probability that A and C fail. I can extend this tree down, but I'm going to be lazy because I don't want to extend the tree down, because I know that A and B, B and C, A and C, that's a 1 out of 2 vote. So I'm just going to use the 1 out of 2 equation, which is, oh, my mind is going blank, lambda squared t squared over 3. Now, this is lambda squared t squared over 3. This is lambda squared t squared over 3. This is lambda squared t squared over 3. I have an OR gate. What did we learn about OR gates? When we're doing probability addition, we don't need to worry about our average before logic, average after logic. We simply do the addition. So I've got lambda squared t squared over 3 plus lambda squared t squared over 3 plus lambda squared t squared over 3, which equals 3 times lambda squared t squared over 3, which is lambda squared t squared. So if we look at our dangerous undetected term in the 2 out of 3 voting arrangement, it is lambda squared t squared. Going through the rest of the terms, beta factor term never changes. I've already explained why you should use TD over TI regardless of what the voting arrangement is. The never detected term always follows the dangerous undetected term in terms of the format. And then with the dangerous detected term, you're going to use similar probability math when you're doing those equations. And with that is where the PFD equations came from. Those are the ones that are used in the ISA training, and those are also the ones that are going to be used in our Vertigo software.